review from last year with geometry, but number 54 is one. I mean, that one was not from last year, but they gave us this equation, and they want to know about the quadratic formula, if we could use that to help us solve it. The biggest thing on this was the equation they gave you wasn't quadratic initially. So you may have thought, well, how do I use quadratic formula if it's not a quadratic equation? Because remember, a quadratic equation really doesn't have an exponent anything bigger than 2. However, whenever we look at these types of equations, we always think about factoring first, even before we think about quadratic formula. And if I look at this, and we could actually factor something out of each of those terms. What can we factor out of all those, right? Yeah, so I can pull an x out of each of those terms. Which means really I already have one of my answers. Because if this is going to work, if x times something has to equal 0, one of my possible answers is x equals 0. So I already have one of my solutions. However, I need to still attack the other part. And this is where the quadratic formula comes in. You could check to see if you could graph or you could factor that, but this one we couldn't factor. So yeah, we can use the quadratic formula at this point because I do have an exponent of 2 there as my largest. So from there, I just plug it in and see what my values are when I use the quadratic formula. All that's over 2a. And so once you plug that in and find your solutions, those would be our other 2 answers. Is there something in the equation that would have told me I would have got 3 answers, or could have gotten 3 answers? What about that original equation would tell me, okay, it's possible that you're going to get 3 answers? Yeah, the exponent being 3. Doesn't guarantee that I have 3 answers, but I could have 3 answers. Just like when we have an exponent of 2, we don't always have 2 answers, but I can't go over 2 answers. I could end up with that. According to what they had, yeah, they just left it like this. So you could punch it in if you wanted the decimal amount. Those are other 2 sources. The other ones, like I said, were mainly some review on a couple things with geometry. 58 gave us this picture, and they said if I took that and spun it around the y-axis, first of all, what kind of shape would I end up with? Well, if I spin that around fast enough, I know at the top I'm going to have a circle. I've got a height here of 5, or yeah, 5, so it's -2 to 3. So I've got this rectangle that has a height of 5 that gets spun around. So what do I end up with? Cylinder, yeah. So I end up with a cylinder. And we already know the height is 5. As I spin it around, what would be the length of my radius for that circle? I'm spinning around the y-axis. Yeah, because that's how far away from the y-axis that rectangle was. So really you're looking at that shape, that cylinder. Then to find your volume, you may or may not have remembered from last year, but it's the area of the base, IR squared, times the height. So in this case, you would have 45 pi. Then the last one that you guys marked were these 2 on number 62. This is going back to some trig ideas. The first one wanted us to figure out the measure of angle B when they gave us 2 sides. So I still start out with the questions of, well, what sides do I have? Do I have opposite? Do I have adjacent? Do I have hypotenuse? So if I'm looking at angle B, I've got the opposite and I've got the adjacent. So should I be thinking about sine or cosine or tangent here? Tangent. So if I'm missing the angle, remember this is where I do the inverse. So I do the inverse tangent of the opposite side of 4 divided by the adjacent side of 5. And once I punch that in, that would tell me what the measure for B was. So B was about 39. Then the last one, we could use a cosine situation here if we wanted to, because I've got the adjacent side marked and I've got the hypotenuse marked. But I also have 30, 60, 90 triangle. So if you remembered your relationships in 30, 60, 90s, we're going to use this. Second semester, we're going to come back to this because we do some things with sines and cosines and tangents. But if I use my 30, 60, 90, remember the side across from the 30 is half as long as the hypotenuse. So it would have been 5. And then we take that short side times the square root of 3 to find the last side. So really side A should have been 5 square root of 3. Now, if you did the cosine, you could still get to a value. It just wouldn't be an exact value, but a decimal value. So like I said, those are the ones that were marked from the other day. A lot of geometry review on that one. All right, to get us going today, and kind of lead into what we're going to do today, I got 3 things that I'd like you to try. This is all going back to the shifting that we did last week. So what I'd like you to try to do, now each situation is its own situation. So once you do part A, you're done with part A. You start over, go back to the original. But we said that our parent graph for a quadratic would be this, y equals x squared. I want you to write a new equation that would take care of each of those different situations. So in part A, the only thing I want to change is I want it to shift down. Part B, again, we're starting all over, but the 2 things I want to have happen is shift to the left 3, shift up 2, and so on. Okay? So go ahead and see if you can come up with new equations for those.
Wait, can you look at my calculator?
You get a different answer.
Like I put in the inverse of tangent of that. It gave me like 0.6.
You get it. Okay. Yeah, you're in a different mode. Yeah, you're in reading mode. Yeah, I should mention that.
That's why.
Think about how you could write those. Probably graphing form would be the best form of having it. Those are actually the first 3 on that paper that I just gave you, so you can write them on there as well. Okay, here's what I'd like you to do. Go ahead and move into your groups and compare just those three right now. Don't move on from there. All right, because I want to talk about how I want you to attack things from there. But go ahead and move into your groups, compare the three equations you got for A, B, and C, and then we'll see where we're headed from there.
Okay, that's what I got. Let's go to the next one. Oh, okay. I was like, the negative pi threw me off there. Oh, crap. Okay, I didn't. Okay,
Well, I tried to do it.
Alright, yeah.
I didn't do it before the report.
All right, let's see what you came up with on these three. Middle group here, what do you have for the first equation?
The y was x squared minus 7.
Right. If I kept it in graphing form, is that the only option for that one? That's the only way we can shift it down 7. Yeah. Okay, so everybody should have the same one for that. Okay, what about part B? This group here, what do you have for part B on here? Good. If I kept it in graphing form, is that the only way I could write that one? Yeah. The only way I can shift it left is to do x plus 3 in parentheses. The only way I can shift it up is to add 2 after we squared it. All right. Then the last one, we had a lot of different things going on there. Group in the back, what did you come up with there? Yeah.
We got y equals -2 multiplied by x minus 2 minus 3.
Okay, so let's check this. The shifting horizontally part to the right would be x minus 2, so that looks good. Going down 3 would be subtracting 3 after we squared it, so that's good. Stretching vertically has to be bigger than 1, so that looks good. And opening downward would be a negative, so that looks good. That's the only way we could write that one if we kept it in graphic form. No, what's the value that could change? A value, right. As long as we stay bigger than 1, we're okay on that. All right, but that was a good option. All right, hopefully we're feeling pretty good about that. On Wednesday, I would expect you to know how to do that. Okay, I would expect you to know how to deal with problems. Today, though, we're going to extend it out and we're going to look at some other graphs. And we're going to see, well, how can I move around some different parent graphs? So the parent graphs you're going to start with, you're going to look at the parent graph for y equals x cubed is one of the graphs you're going to look at. A second one you're going to look at is y equals the square root of x. And then the last one you're going to look at is y equals the absolute value of x. Now, as you're doing these, initially you've got to know what those graphs look like. So before we can start moving them around and then making changes to them, we got to know what the parent graph looks like. So just like when we started with the parabolas, it's okay to use your calculator for that. Okay, so it's okay to plug it in and see what your graphs look like. When you make your sketches, though, make sure that you label any key points. Like when we did our y equals x squared, we said, well, the key point was the vertex. You got to make sure we have that labeled. And then we needed enough points to have a good shape after that. Same deal here. There should be some sort of point that jumps out at you like, okay, this seems like an important point, and then have enough other points where it can make a good graph. Okay, so kind of keep that in mind as you're making your sketches. Secondly, when you get to the last equation, finding the absolute value on the calculator, sometimes it seems like it's a little bit hidden. The absolute value is under the math button. So under the math button, you have to go to number, and it's the first option, ABS. Okay, So when you get to the absolute value part, that's where that's found under the math. Okay? All right, so I'd like you to work with your group members. I'd like you to stay together here as you're working through because I want to make sure we're getting the same graph and we're able to make the same changes as we go through. Okay, so stay together as you're working through and then we'll see what sort of things you did for those different equations.
I should do one video.
Again, if you're making your graphs and making your changes, compare, make sure everybody's making the same graphs.
Oh, yeah, like, worse.
Yeah. Yeah, I can see that now. X minus 2, well, nothing else.
Yeah.
Yeah, because I want to get a high school, because I used to have a school that just went last.
Wait, what's your name?
So I'm bigger than my
X minus 2
school.
why, you know, Billy Boy, X minus 2.
I still love it more. And either way, high school is- You obviously have your glasses. But this is like a little cool. Maybe because you squatted, because your next is just if I use it slowly, on the same train,
So you're gonna. Oh.
Yeah, I just think going like glass.
When you're doing your current graphs, try to get the shape as accurate as possible.
Yep, thank you.
You need me to sign your pass.
No, it's fine.
Then enter. Yes.
Okay, let's try to wrap up in the next couple of minutes. As we attack these new equations, new situations, what I would like you to be able to do is, first of all, identify what the shape is. So if I gave you an equation that had an x cubed in there somewhere, I would expect you to know what a cubic looks like. It's going to have the shape that is like the graph that's up there. Same thing for the square root of x, same thing for absolute value of x. Because before I can move stuff around, I got to know what I started with. Okay, so you should know those. Now, in terms of the test on Wednesday, you won't have any of these graphs on there Wednesday. The parabolas, yes, but these, not quite yet. But by the end of this chapter, by the end of the full chapter, you should know what all these graphs look like. Secondly, we should know what the important points are for each graph as well. So when I start shifting things around, yeah, the whole graph shifts, but I'm really going to just focus on this one point that's going to shift. And again, like I said, for the parabola, that was the vertex. Let's see if we can identify what it is for these other graphs. So if I look at this first graph, this cubic, and I tried to identify what I thought might be a main point of that cubic. What do you think might be an important point of this cubic there? Helen? Okay, what would you consider that to be? Okay, so kind of where it had this shape and it turned a little bit and then it continued up in the other direction. So where's it located right now on the parent graph? Yeah, right at the origin. It's kind of where that changeover took place. That point actually has a name. It's referred to as the inflection point of that graph. The book usually is going to refer to that as the locator point of the graph, though. So if they ever ask you where's the locator point, for a cubic at least, that would be the locator point. But it's really where that change took place, where we're kind of heading up, we headed over a little bit, and we started heading up again. The book would consider the vertex of a parabola the locator point of the parabola. Where do you think the locator point is for the square root of x in its graph? What might be an important part? Yeah, the origin again. So the locator point here is at 0, 0 because that's where it started. And a lot of times that's what I just refer to it as. It's the starting point. So it's the starting point of my square root graph. What about the locator point of our absolute value? The vertex, which is where on this one, 0, 0 again. So the nice thing was all three of these, the locator point was at the origin. We'll look at a graph where that's not the case later on, but for all three of these, the locator point is at the origin. The other nice thing about the absolute value graph is it's very similar to our parabolas that we've already dealt with, other than now we have that V-shape going on. All right, so once we know what they look like, we got to know how to move them around. Well, the nice thing was when you moved them left, right, up, down, all those movements, was that any different than we did before? No. If I wanted to move, say, this square root graph 3 units to the left, well, I would have to add 3 to my x value underneath the square root. That would move it 3 units to the left. What if I also wanted to move it down 5? What would I have to do? Subtract 5 on the outside. So no different than what we've been doing before. So all those movements that we did before, those remain the same. Some things that might be a little different, though, would be, what if I throw that coefficient out the front? Like for the cubic, I think I asked you about 4x cubed. Is that right? Is that what I asked you? It's 4x cubed.
Yeah.
Okay. So would 4x cubed, would it be more like this blue graph? Would it be more like this red graph? Which one do you think would be more like the 4x cubed? That situation. Yeah, the blue one. All right. We said whenever we had a coefficient, say of 4, something bigger than 1, when we did parabolas, that made that parabola narrower. Well, it's kind of hard to decide how wide or narrow a cubic is. So maybe we ought to describe it a little bit differently. So here's what we might think about. Is that graph getting closer to the y-axis or getting further away from the y-axis? Well, if we have that 4, what happened? Did it get closer or further away? Closer, right? And that's why it became narrower when we had that parabola. But for some of these graphs, it's hard to decide narrowness and wideness. So maybe we think about that instead. Well, when I stretch it vertically, it gets closer to the y-axis. So what happened when you did this graph, and I think I asked for 0.3 square root of x? Because you can't really, again, decide if it's narrower or if it's wider. Well, 0.3, would that make it get closer to the y-axis, get further away from the y-axis? We said a second ago the 4 got me closer to the y-axis. Should be further away, right? So I'm getting further away from that y-axis, which in this case, if I'm compressing it, means I'm getting closer to the x-axis. So it still looks a little bit flatter, still the same shape, but I've compressed it down. But technically, it's gotten further away from the y-axis. Had I given you a value bigger than 1, it would have got closer. It would have been stretched out more this direction, maybe, for that. So sometimes those get a little bit confusing. Absolute values usually aren't too bad because they're just like parabolas. I didn't give you any like this, but what if I threw some negatives in? What would happen if I said, okay, graph y equals negative x cubed? We know what happened with the parabola. What's going to happen with this?
It would be flipped along the y-axis.
So we're going to flip it this way.
Yeah.
When I had the parabola and I did a negative x squared for the parabola,
So yeah, it would cross there.
yeah, we're going to go the other direction. So we didn't go that way, but we actually went that way. Same idea here. Now it's going to look like you went across the y-axis, but it would look like this because really we're reflecting over the x-axis on that one. Same deal if I were to say, okay, what's the graph of y equals negative square root of x? Well, now I'm going to take that, and again, I'm going to reflect it over the x-axis. So it's going to look almost like another side of a parabola if we piece it together with the first one. Okay, so the negative just means I reflect. So we got to know what these look like, and then we got to be able to make some changes to those. I'm going to give you 2 others. So first of all, just come up with, well, actually, let's look at these first. This would go with that last page with the absolute values. Which one of those graphs up here, 1, 2, or 3, which one of those graphs would be the example for y equals 3 times the absolute value of x minus 2 on that one? 1, 2, or 3? Joe? Yeah, second graph. Because where should the vertex be? Yeah, 0, 2. The 3 told me it was a little bit narrower. than the other one. So that should have been the graph for A. What'd I say? Oh, yeah, 2, 0. Thanks. What about for B? Which one of those would be y equals negative 0.2 absolute value of x plus 5? Yeah, and that's got to be because it's the only one that was opening downward, right? It's also wider because of that 0.2. And then the last one, we should have a vertex of -8, -9, and then it was opening upwards. So that's why it would have matched. See? All right, but again, usually the absolute values aren't too bad. All right, on the back side, here's what I'd like you to do. I want you to sketch, first of all, these two parent equations. So one of them is this hyperbola, y equals 1 over x. The second one is the exponential y equals 2 to the x. So graph those and sketch those. Both of them include some asymptotes, so try to identify where the asymptotes are. Y equals 1 over x, you got two asymptotes. You should have one asymptote for the exponential. Make sure you mark your asymptotes on the graph with dotted line. You should have a graph that looks like this for the parent equation of 1 over x. Again, the two asymptotes that I'd expect you to label on the parent graph actually turned out to be the two axes, y-axis, x-axis, where y equals 0 and x equals 0. The locator point that we're going to use for hyperbola, because we're just doing sketches, the locator point is actually not one of the points on the graph. The locator point that we're going to use is the intersection of those two asymptotes. So the intersection of these two asymptotes right now is at the origin. So if I start making adjustments or movements to this graph, for instance, if I ask you to sketch the graph of this, y equals 1 over x minus 2 plus 3. And I ask you to do that without a calculator or without any technology. Well, what I'd want to think about, first of all, is what kind of movements are taking place. Well, just like every other graph, in a situation like this, tells me I'm going to shift left or right a certain amount. So first of all, which direction are we going there? To the right. So I'm going to move this graph to the right 2 units. Then after that, it says I'm going to move it up 3 units. Well, what that means is my locator point is now going to shift from 0, 0 to 2, 3. So the intersection of my two asymptotes should be at x equals 2, which makes sense because at x equals 2, that one's undefined. We said that's why we have a vertical asymptote. And then up 3, so a horizontal asymptote at 3. So if I asked you to sketch it, I'd want you to clearly show that you had x equals 2 for an asymptote and y equals 3 as an asymptote. From there, the graph is just that. It's a sketch, and we know the shape of it. So we're going to get close to this asymptote, close to that asymptote. Same thing here, close to those two asymptotes. Okay? So if I ask you to make that sketch, that's something that I'd be looking for. But really, the locator point becomes, in this case, 2, 3 because of those shifts. What about the exponential? Where was the asymptote for the exponential? 2 to the x. There's a horizontal asymptote on this one.
It was y equals 0.
Yeah, it's just the x-axis, y equals 0. Then from there, we had this graph that was close to the asymptote, and then it kind of took off here at this point. And that's going to be the locator point. So our locator point for our exponential is at 0, 1. I just kind of call it the takeoff point. That's where it was kind of leveled out, but then it hit that point and started increasing fairly quickly. So let's see how we might make a change to that parent equation. So let's say I gave you this, y equals 2 to the x minus 1 power plus 4. Well, whenever you sketch your graph, the two things I'd want to see is where's your asymptote at, and then where's that takeoff point at. So let's start with the asymptote. According to this equation, we're shifting up 4 units. So it actually tells me where the asymptote is right there. So I would start with that. I'd start with a horizontal asymptote of 4. The second thing I want is where's the locator point or that takeoff point at. Well, originally it was at 0, 1. We've already moved it up 4 units because of this. So right now it would be at 0, 5. However, what's this say to do? Move it left or right? To the right. So my locator point or takeoff point now is at the point 1, 5. So my sketch is going to look similar, except now it's shifted over a little bit. It doesn't start increasing until we get to that takeoff point of 1, 5. So those two are a little bit more difficult. We'll work on those, but those are going to have some special situations with the asymptotes on them. But again, our shifts and all that sort of thing, it doesn't matter what graph we're looking at, they're essentially going to be the same from our equation, right? We're thinking about shifting left and right when we deal with the x. We're thinking about up and down after we've done the operations. So hold on to that paper, have that paper in your binder, because we will reference that later on. All right, I'm going to give you the review sheet to start working on. This will give you an idea of main topics for our test on Wednesday.
Is that stuff gonna be on the test?
No, not yet. Yeah, today's stuff will not be on there in the mid-chapter test. Parabola stuff will be. So this will be an assignment for Wednesday. Don't submit it electronically though. I'll just look at your hard copy on Wednesday. There's an assignment set up online, but that's really for the students that have a great attraction.
So what? We're dealing with travel. How do we move it for an operation? Oh, so, yeah, I might have it. Okay, I was just shooting now. Thank you.